Hi, everyone. Thank you so much for coming. My name is Noah Lubin, and I recently graduated from Bar-Ilan University, just finished my master's. I'm going to discuss a joint work with Jacob Goldberger and Yoav Goldberger, who was my advisor. And it's a work published at NACL 2019. And let's start. So in my thesis, I focused on noise in NLP problems. So as you all know, it's very hard to get labeled data set. And often when we do get labeled data set, the set contains noise in the form of incorrect labels. Specifically, the microphone is like on and... Okay. Do you hear me better? So I specifically focused on the alignment task. So let's understand what does the alignment task mean. So in this task, we're giving two vector spaces. In my example, vector space X is Spanish word embeddings, and vector space Y are English word embeddings, and they were created completely independently. And what we know is that there is an alignment, a matrix multiplication of this vector space that can align the entire vector space on top of the other one. So my goal is to find this Q, which is called the translation matrix, and apply it on vector space X in order to land on top of vector space Y. So how do we do that? How do we find this translation matrix? This is a setup that Mikolov created in 2013, just as soon as he created Word2Vec. So like in the previous example, if we have the Spanish word embeddings and the English word embeddings, and we're giving a very, very small lexicon, a lexicon is like a small dictionary that contains pairs of both embedding spaces. It can be very small, just a few thousand example, or have not exist at all. By having this lexicon, I can learn the translation matrix. How do I do it? I minimize this loss function. I minimize the Euclidean distance between the vector space X after applying the transformation and vector space Y on top of the lexicon. So there are two methods that did this. The current methods who do this are, first of all, gradient-based methods, all that you guys know, gradient descent. Also, it can be a Newton method, any gradient-based method. And another method is called orthogonal procrustes. It's a method where Q has another restriction. It needs to be orthogonal. And this was found to be correct for word embedding translations. So I looked at these two methods and I asked myself, what happens if I introduce to these methods some kind of noise? What do I mean by noise? I mean noise that are incorrect pairs in this very small lexicon. So why do I even expect incorrect pairs in the lexicon? These are the three main reasons. So the first reason is polysemy. In languages, we have multiple meanings for the same word. So if I want to project one word that has several meanings on top of a word in another language, I need to choose the best fitted one. Also, we have the problem of same string pairs. For example, if I translate the New York Times proper noun to Spanish, for example, usually it will appear as the same proper noun, the New York Times. Therefore, the translation of the word new to new might appear in the lexicon. The third reason is the embeddings themselves. We use these methods usually for very low resource languages, languages that we don't have a lot of text for or don't have a lot of labeled data for. And the embeddings themselves can be trained upon very small data and therefore contain a lot of noise. So these are the three reasons that I did expect to find noise, and we will see it in the real world experiments. But first, I asked myself, what is the effect of noise? So I did a synthetic experiment. I took 10 two-dimensional points in order to visualize it better. And I randomly selected an orthogonal transformation and applied it on the data set. And then I used the two methods in order to learn the translation matrix. And when there is no noise applied, the translation is learned perfectly, and they line one on top of the other in both methods. But what happened when I took only one pair and misplaced its partner? The entire alignment fell apart. The learned matrix in both methods was completely, not completely, but very incorrect and resulted in incorrect translations. And later I performed this experiment in a higher dimension using glove word embeddings and saw the same phenomena, that even a very small noise in my lexicon can result in a very bad translation matrix. So I proposed a solution, which is, I think, very intuitive. It's a generative model that both identifies the noisy pairs in the lexicon, and once it identifies the noisy pairs, it ignores them while learning the alignment matrix. And how do we do it? We do it with a generative model. So for those who haven't heard of a generative model, we tell a story of how these vectors were created. So the story is this. I toss a coin with probability alpha, which is one of my parameters. And if this coin lands on 0, I assume that the word vector was created with a normal distribution with expectancy mu y and with sigma y squared divergence. And if my coin lands on 1, I assume that the pair is still aligned, and then the normal distribution is with expectancy of qx and a different sigma, which I expect to be a lot smaller. So all these parameters are learned together in a form of an EM algorithm. So in the EM algorithm, I'm not going to show you the algorithm itself, but I'm going to explain the general idea. So the general idea is that in the E step, we identify the noisy pairs, we calculate our latent variable, and in the M step, we learn the projection based on the clean data set and the other parameters. So once I had this solution in my hand, I wanted to see how it improves current NLP tasks. And I did it on two very different tasks. So the first task is, like we saw in the first example, bilingual word embeddings. So if I have word embeddings in two different languages, in this example, general language A and general language B, and now it's a bit different because I used the totally unsupervised setup where no lexicon is given at all. It's a setup that Artechte built in 2018. And it works such a way that the lexicon is first calculated based on similarity of word embeddings. And then we learn a new mapping. We expand our lexicon, and then throw randomly words from the lexicon. And then this process goes on repeatedly until a convergence occurs. So I replaced the mapping which was used in the current previous methods, orthogonal procrustes. I replaced it with my model, and I want to see improvement both quantitatively and qualitatively. So the quality analysis, I showed you a few examples. So of pairs that my algorithm classifies as noise. So in the bottom, you can see what we talked about earlier, that the pairs new and new in Italian and New York were classified as noise. And as we all know, we don't even need to know Italian. These are incorrect translation. But the pair new nove was classified as aligned and therefore used in order to learn the translation matrix. Also, you can see the translation of the word good to bon and bona, which were considered aligned. But the translation good santo was considered as noise. So if there are any Italian speakers in the crowd, they may know that santo is indeed a good translation for the word good. But because we want to learn an alignment that is cohesive, our algorithm chose the best translation or the most probable translation, which is bon and bona. Also, when looking at the numbers, we improved the precision at one score for 4 different translations from English to Italian, German, Finnish, and Spanish. And also, our algorithm took a lot less iterations in order to converge. Now, we wanted to discuss a totally different task, and we'll soon see how is it related to the noise-aware model I created, and it's the historical word embeddings. So in this task, we want to know if a word changed its semantic meaning throughout history. So for example, the word gay in the 1900s was more related to happiness and cheerfulness, but nowadays, when someone says gay, he mostly refers to homosexuality or something related to this field. So I want an automatic way to recognize those words who's shifted semantically. How are we going to do it? So again, we have 2 vector spaces, one of English word embeddings from the 1990s, and one of English word embeddings from the 1900s. Now, my lexicon is just every word mapped to itself. Why? Because I still assume that most words in the language didn't change their semantic meaning. But please notice that if I look at every word mapped to itself, I assume that some of them are noisy, because I assume that some of them did change their semantic meaning and won't fall one on top of the other. So by using my algorithm and looking for the noise, what it considers as noise, I can definitely say that this might be a semantic shift. So I used a setup done by Hamilton in 2016, and he gave the words to language specialists, which indeed confirmed that these are words that have shifted their semantic meaning. And my algorithm identified all of the words that shifted their semantic meaning, which was very impressive to see and very fun to see. And in addition to that, it created a better alignment if I look at it as a translation between the time periods. So I gave you a few examples. For example, the word wanting, which was in the history more related to lacking, and nowadays is more related to desiring, was more correctly mapped to wishing than need. And the word actually, whose meaning has shifted from a very objective statement to a very subjective statement nowadays, is also more correctly mapped to really instead of believed. And in addition, words who haven't changed their semantic meanings, for example, the word car, are still mapped to car and not to cab, like we saw in the synthetic experiment, that incorrect translation pairs can cause a total misalignment of the entire setup. So I want to sum up. In my work, we saw that the current methods are sensitive to noise in the form of incorrect word translation. I saw that noise does exist in real NLP problems and proposed a solution to solve it. And if you do any sort of alignment, it might not even be related to language. I highly encourage you to use my code. It's available and it's very easy to use. Also, if you're interested in alignment or other NLP problems, please feel free to reach me in my LinkedIn page. Thank you, guys.